All right. So I'm going to continue where I left off last night. I was doing a tutorial on... I'm just going through the Entagma tutorials to get better at... to get a better understanding of how Houdini works. So yeah, let's continue.
Underscore here, neighbors, and we need brackets here to indicate that this is an array attribute. And now we use poly neighbors.
Integer poly neighbors. So I think this is how you define a variable. Let's see, where's my Houdini window? There's my Houdini window. Int poly neighbors. Equals poly neighbors.
So geometry string 0, and the primitive that we want to use for our search is primnum, the currently processed primitive.
0, comma, prim num, parentheses, semicolon.
We want to choose the neighboring polygon that has the highest ID. So let's first create a variable of type integer called parent. And let's initialize it with -1, indicating that this is not yet a usable index. And now we do it for each loop. Because we want to loop through all found neighbors. So for each neighbor, and then poly neighbors, which is the array. Brackets, like so, and inside of this loop we want to do an if statement to compare the currently processed neighbors index to parent, the variable we just used. So if the neighboring index is bigger than whatever we have in parent, then and only then, curly brackets, we want to update parent with NBR. So this logic says, please start with the very first neighbor.
So we do another little bracket here, tab it. Parent equals neighbor. Parent equals neighbor. So create an integer poly neighbors equals poly neighbors 0 at primitive number. Int parent equals -1 for each integer number.
If its index is bigger than -1 and all indices are, then put it into parent and go to the next neighbor. If the index is bigger again, then put it into parent. If not, do nothing. So after this loop finishes, we have the biggest neighbor, or the neighbor with the biggest index. But there's one thing that we want to add here in the if statement. We need a logical AND because we want to test another condition, and that is the neighboring number should at the same time be bigger than the prim num. So
Ampersand, ampersand, number is also greater than the primitive number.
We only want to search for indices that are bigger than our own index. Great. So now after this loop, the parent variable will hold the correct parent for our primitive. So let's write it to a primitive attribute of type integer. So I add parent, and this will be parent. Like so. Let's test. No errors so far. Make this visible.
Parent equals parent.
Go to spreadsheet and then to polygon, and we see, okay, we have parents here, and some of the primitives have a parent of -1, and that means
Okay.
that these polygons don't have a neighbor that has a bigger index than themselves. Okay, cool. Now we have the parents. And that would be sufficient if we could use recursion to go through all these primitives and find the correct order. But we cannot, unfortunately, as Vex does not support recursion. So what we have to do instead is to find all
no recursion
parents for each individual primitive. So each primitive has to know all the parents up to a primitive that has -1 as a parent, which is basically a root primitive. The next thing we want to do is gather all the parents. This fortunately is not very complicated. We just need another wrangle, a primitive wrangle. Find it here, and let's call this one gather parents. Gather parents, make it visible, and let's find all the parents for each individual primitive. First we'll need some variables, so an integer called parent, which we initialize.
variable called parents that we initialize
With 0, then an integer called index, ix, which will initially be the prime1, and then an integer array, the parents. This is our result array. And now we want to do stuff while parent is bigger or equal to 0. So that means as long as the parent we find will not be -1, the loop will continue. As soon as the parent index will be -1, the loop will stop. And that is exactly what we intend, because primitives with a parent index of -1 are root primitives, and there the chain stops. So now let's first import the parent. So parent. We don't have to initialize the variable here because we already did so in front of the loop. Prim is 0, the attribute to look up is parent, and idx is the index. So we will start with the currently processed primitive and find its parent. And now we append this to the array. So append, the array is parents, and we want to append parent. Now the first parent is appended to the array. And now we want to make index the parent index. And this means that now the loop in the next iteration uses the parent of parent, so the next parent. And it will just continue through the entire object until it finds a primitive with a parent index of -1. Then it will stop. So after this loop we have an array with all the parents. So let's say I, and then brackets. This is the syntax for creating an array attribute. Let's call it parents again, not to confuse stuff, and let's fill it with the parents array. So let's see what this gives. Let's press apply and accept. Make this visible and go to the geometry spreadsheet, and here we have our array. If I extend this here, you see that all the primitives have a parent array, and of course these.
I did something wrong. Let's go back and see. parent equals prim 0 parent idx parents prim num parent equals well, that might be it. Syntax error occurred, expected, unexpected, expecting what? What did it say? Expected the column.
Very high primitives have a short wheel. It's up to.
Oh, he used an underscore.
Loop primitive that has -1 as let's make it rect or have a neck primitive. Okay, no error. Parent. Like so.
All right, let me check this. Under poly neighbors. How come my poly neighbors isn't blue? Parent -1. Poly neighbors. NBR. Parent and NBR. Prim num. Oh. At prim num. Still an error, okay. Yeah, prim num, parent NBR, error. Okay, it says the error down here. And it says invalid attribute VOP, error in VOP snippet 1. Object find parent attribute VOP 1 snippet 1 call to undefined function polyneighbors. This part? Where is that? Did you mean neighbors? Maybe. Neighbors. So what happens if I just change all the neighbors? Reference to undefined poly neighbors. Okay. Invalid. Object Geo1 find parent. Attrib vop. Reference to undefined variable primnum. Aha! Okay, cool. So now it shows up with all that. Excellent. Now, this one. This one. Parent IDX at primnum. Parents, while parents greater than or equal to 0. Parent equals prim 0 parent IDX. Parents IDX parent. Oh, okay, there's no errors. Okay, cool. Very good. Okay, now we've got that.
Press apply and accept. Makes this visible and go to the geometry spreadsheet. And here we have our array. If I extend this here, you see that all the primitives have a parent array, and of course these very high primitives have a short parent array because they are close to the.
How do I see that? View, show all attributes. Map offset. I don't have those. Distance. You should be able to see parent in parents. Parent equals. Well, let's see if it works anyways. Even though I can't see the parent variable.
First primitive have a very long array because they are not close to the root primitive. And this array contains all the parents. But there is a flaw with all these arrays, and that is that we have an index of -1 in all of these arrays. And for later use, we don't want this index, so we somehow want to remove this index of -1. We can achieve this by, before we write the array to the attribute, let's first say parents is reverse. We just reverse the order of the array such that all these -1s are in the very first spot. And now we say remove index. Remove one index from the array. The array is parents. And then it's removed with 0. Now we remove the -1. And if we have a look at the array now, of course the order is inverted, but at the same time all the -1s are gone. And primitives that are root primitives, because they have a parent index of -1 already, don't have any parents in the array, so the array length is 0. Next step, the next step, now that we have,
I'm gonna have to go back and watch this probably.
Structure is to create a matrix.
Fix my
so
code.
Transformation system. We want to put each individual primitive into its own coordinate space, basically. So we want to create a 4x4 matrix for all the primitives that specifies the global transform for this primitive when seen as an object. The very first step in creating such a system is to find the edge between the primitive and its parent, because eventually it should rotate around this edge. So we have to place the origin of the new coordinate system here in the middle of this edge. So if we are looking at 726, here should be the origin of this system. So before we are dealing with matrices, let's first find this edge. And how can we find this edge? The easiest method is, as we're dealing with triangles, to look at the points, and this edge has 2 points, and these points are the same points in both triangles. So that is a criterion to find this edge. So let's implement this. Let's lay down another primitive wrangle, and let's call this one find edge points. Find edge points, and let's implement this. Let's find the edge points. Well, first we need all the points of the primitive and its parent. So in my points, this is an array, will be prim points, geometry speed 0, and then myself, so prim 1. This will give all the points that are inside of the primitive that is currently processed. And now we need the exactly same information about the parent. So int par points, parent points, another array, prim points 0. This time we use the parent ID, and the parent ID is saved to an attribute already, so we can use this attribute I add parent. Like so. Now we have 2 arrays containing the points of the primitive and its parent. Now let's create the result array int edge points. Let's stay consistent and say points here, brackets, and I'm going to initialize this one. And now let's do a for each. For each, we want to run through all the points of the currently processed primitive. So int point, my points, separate, like so. And now we want to do a second for each loop, because for every point of the currently processed primitive, we want to test all the points of the parent primitive. So another for each loop, for each, but this time running over the par point of the par points array. And brackets. And now we can say if point, so the point inside of the currently processed primitive, is exactly the same as par 20, so the point from the parent primitive, then append this point to our edge points array. And key should be appended, like so. Great, so this will find
Easy.
points that are the same in both arrays.
Simple, really.
And now let's create another array attribute. I, in the brackets, add edge points. Edge points. Cool. Let's test this. Apply, accept. No errors so far. Go to the keep.
All right, let me make sure my thing matches his. I edge points equals edge points. Okay. Int my point equals print points. Int par points. Hi at parents, edge points for each, int point my points for each int par points par points points par point pen edge points okay. It says error in VOP snippet 1. So that's still happening. Find edge points. Attribute. VOP snippet 1. Syntax error unexpected identifier. Aha! Missing a bracket here. I've got 2 parentheses there. My points for each int par points par points if point equals PowerPoint pen edge points I equals at edge points equals edge points. Okay.
Little spreadsheet. Here are the parent and here are the edge points. Okay, 0 edge points. Let's see if this worked. Let's quickly find primitive 0. Should be over here. There it is. Let's turn on point numbers. And the points are, well, first we have to see which parent it has. It is 5. 5 is the parent. So the points found should be 3832 and 3060. And it found 3832 3060. Seems to work. So it.
Alright, where's my 0 point at? How did he find it so quick? There it is. Okay.
Found these 2 points, and with these 2 points we have this vector between them, and that is the edge. So after this wrangle we have the edge between each individual primitive and its parent. But wait a second, what happens to root polygons? Let's see if we can quickly find one. So if I go to parent, here I have -1, and you see now we have an empty array. And an empty array is a good thing here because we need this vector for building the matrix. So we have to somehow deal with the situation. We have to do an exception for the primitive that has a -1 as a parent ID. So let's quickly do this. Open up the editor again, and let's introduce a special case. So let's correct the order case. If the order case is actually present, smaller than 0. That is the case with all the loop values. Then append to edge points just the very first point of the primitive, right points 0, and let's copy this line. Like so, and let's append 1. So if we don't have a parent, then just use the first 2 points of the primitive. I have an error here, so a typo, edge points. Let's see what it is. Okay, I missed the closing bracket, both of these lines. Like that. And now, although we have a parent ID of -1, we have a
If I parent less than 0, append edge points.
we do have edge points here. Great, so we corrected for this special case. Now it's time to create the matrix. So lay down a new primitive wrangle. And
Another one. Oh my gosh.
let's call it field system. Now the magic happens. So let's build the system. Okay, Alt E again. Let's start by gathering all the necessary information. So first we need a vector which will be edge point, edge position 1. So with a point expression for this, we search 0, that position, and then I add edge points, and the index we need to read is 0. So now this construct here is necessary because edge point is an attribute array, and it is necessary to specify I brackets, oh I forgot an add here, I brackets add to tell the point function that this is an array, otherwise it won't work. And then we want to read index 0 because index 0 is the very first point of the edge. We read the position from this one, and then let's copy the line like so, and this time we want to read edge points 1 because this array only has 2 points. Now that we have these 2 points, we can form the vector between them. So vector edge is edge plus 2 minus edge plus 1. Why edge plus 2 minus 1? Because tails first, so it's pointing to edge plus 2. Now we can create our basis. So for the basis of a transformation matrix, we need 4 vectors. The x, y, and z axis, and the transform, so the origin of the coordinate system. And Houdini uses the convention for the names of these vectors, and that is normal, tangent, and bitangent. So let's start with the bitangent, that is, so to speak, the x-axis. Vector bitangent, and this should be the normalized edge vector. So normalize the edge of first direction for the new matrix. Now we need the normal, but in this case it's the normal of the polygon. So vector normal will just be head n. If you wonder why you don't need a b in front of the add sign here to specify that this is a vector, that is because n is a standard attribute of Houdini, and so Vex knows that this will be a vector. And then vector number 3 is tangent, and that will just be the cross product between bitangent and normal, because the cross product of two vectors gives the vector that is orthogonal to the plane spanned by the two vectors, and that is exactly what we need for an orthogonal matrix. So tangent will be normalize cross from the cross product between right tangent and normal, like so. And last but not least, we need a fourth vector, the vector or the origin. And this origin is just the center point of the edge. And to reach the center point, the formula is edge plus 1. So we start at one of the points, the first point. And now we add the edge vector, but only half of it. So we multiply by 0.5, like so. And this gives exactly the center point of the edge. Now we have our 4 vectors. Time to create a matrix. So let's create a matrix attribute, a matrix. And let's call it xform. And with the set function, you can directly set the 4 vectors of the matrix. So by tangent, normal, tangent, and origin. 4x4 transformation matrices in Houdini work that way. First comes the x-axis, then the y-axis, and the z-axis, and then the transform. Great. And now we can write this to an attribute. So 4 at xform is xform. Like so. Let's see if we did mistakes, and of course we did a lot of them. So vector edge plus 1, I missed to change this to 2, and now everything works. Except, let's get rid of all these numbers and let's check the attribute spreadsheet. And here we have an xform matrix.
Okay, so what's the issue? The issue is undefined variable vector 1, 5, 10. What now? Reference to undefined variable vector
It is composed x-axis, then the y-axis, and the z-axis, and then the transform. Great. And now we can write this to an attribute. So x-axis and then x. So vector edge plus 1, I missed to change this to 2, and now everything.
Oh, I put equals. Okay.
Let's accept. Get rid of all these numbers and let's check the attribute spreadsheet. And here we have an xform matrix. It is composed of 16 floats. Here we have the first vector. 1, 2, 3, 4 components, because all the transformation matrices, of course,
Aha!
are there.
There they are.
And the second vector, 1,
I had to
2,
click
3,
whatever
4.
this button is.
And the fourth vector, 1, 2, 3, 4. And then there's the third vector, and then the origin, 1, 2, 3, 4. But if you deal with transformation matrices a lot, you probably know that they are formulated in homogeneous coordinates. That means they are containing 4 components instead of 3, although it's 3D vectors, not 4D vectors. And the last component, this 1 here, is used to determine if the vector is a rotation vector or if the vector is a translation vector. And to create a proper homogeneous matrix formulated in homogeneous coordinates, these values here these ones for the very first three vectors should be 0, not 1, because these three are the rotation part of the matrix. So we have to somehow set these components to 0, otherwise it won't work. And we can do that. So let's
Easy.
go
I know how to do that.
into our code again. And
Just go into the code.
these components to 0, and we can use the component syntax of matrices with vex for this. So x form dot xa, and that means please target the fourth component of the first vector. So the x refers to the very first vector, and a is the fourth component of this, and this should be a 0 or a 1. Then x form ya, guess it, should be 0, and then x form za should be 0 too, like so. Let's see what this gives, apply and accept, and now these are zeros. There would be, in principle, a lot to say about.
What did I do wrong? XAYAZA. What does it say? Let's check. Expecting semicolon after 7.5. Oh, I added the fork here somehow. Okay.
Gives, apply, and accept.
All right, let's polyfold. Let's fold some polys.
There would be, in principle, a lot to say about homogeneous matrices, and I will do so in a future tutorial. But for now, just take my word that it is necessary to set this fourth component of the rotation vectors to 0 for the whole thing to work. And why has this value been 1 in the first place? Well, because we use standard vector trees. And when Houdini converts a vector 3 into a vector 4, it sets the fourth component to 1, because it assumes it is a point. And that is why we had 1s here, and now we corrected this. So let's check what we have visually. Switch back to the viewport, and let's create a visualizer. A new marker, and the attribute to visualize is x form, and x is.
Wait, where is that? The visualizer?
And y has this value. Switch back to the viewport, and let's create a visualizer.
Back to the viewport. This thing? No. What did you click?
A new marker and
Dude, my left arrow key is broken.
Switch back to the viewport, and let's create
Marker. Redshift viewport.
a visual.
Add scene. Marker. Add scene. Visualizer. Color. Marker. Volume. Tag.
Visualizer.
Marker.
A new marker, and the attribute to visualize is x form, and axis.
X form axis. Do I need something selected here?
If class AutoWorks, show error tips and less. Lengths to the vectors, and you see this is a system that we created. And you see it is orthogonal, which is good, and it is oriented with one of the edges.
Let's go back. What did he have selected? He had this selected.
And why has this value been 1 in the first place? So let's check what we have visually. Switch back to the viewport and let's create a visualizer. A new marker and the attribute to visualize is xform, and axis.
That's what I did. X form, axes, aha, there it is. There we go. All right, cool.
If class AutoWorks, show error tips and less length.
Oh, show arrow tips.
Vectors, and you see this is a system that we created. And you see it is orthogonal, which is good, and it is oriented with one of the edges of the poly. So the red vector is always parallel to one of the edges, especially the edge between the polygon and its parent. But unfortunately, there is another problem, and the problem is that due to the arbitrary ordering of the point numbers, sometimes the red vector is pointing to the left and sometimes it's pointing to the right. What we need is some consistent behavior here. So there should be an order to this direction of the red vector, so the bitangent. It should always point in this direction, for example, no matter what the point order of the edge points is. So we need to come up with a correction for this again. And how can we correct this? Well, we can compare this bitangent vector to the vector that connects the center point of this polygon with the center point of its parent. And this vector should, for example, always point to the left of this vector, or always to the right, but always into the same direction. So let's implement this correction quickly. It's not too bad. We have to do this before we create the matrix, so we have to correct the vectors. So let's introduce a new section called direction correction. So first let's get the parent position, so the vector. Let's call it parPos, and let's use a prim expression or a prim function on geometry screen 0 to get the position of I at parent. That is the position of our parent. And now we can form the vector between our own position and the position of the parent. So vector pardir, or parent direction, is p, which is our current position, minus our plus. So, and now we can use the dot product between this vector and the bitangent tangent to see if it is oriented correctly or not. Because the tangent is the vector that points in the direction between the two triangles. And if it is pointing in the same direction as the vector connecting the two, then the dot product will be positive. If it points in the opposite direction, the dot product will be negative. So we can use a dot product between these two vectors to do a test. So let's write if dot tangent is pardir parent direction is smaller than 0. So if the tangent is looking into the wrong direction, so to speak, if this is the case, then please invert tangent. Tangent times equals -1. Like so. And if I now press apply, you see some of these have switched. Let me undo this by quickly commenting this out. You see, these switched. And if I do this again, they switch again. And now they are pointing always into the same direction, basically.
Okay, what did I do wrong? Let's see, par pose equals at prim 0 I parent. If dot tangent direction correction. 1349. All right here. Thirteen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Right here. Oh, I have 2 of these boys.
Guarding the parent, of course. Okay, now that we have that, apply and accept, and we are done with the system. So I think we reached a milestone here because we created a global coordinate system for each individual primitive. So we converted this object to consist of little objects, so to speak, because each primitive now has its own transformation matrix, just like an object on the scene level. That is a milestone. That is the most important part with the entire effect. But to reach our final goal of curling this up and splitting it up, there are still a lot of wrangles to be implemented. And that's why I think it's best to wrap it up here, call this part 1, and
there's a part 2?
Part very soon that shows the rest of the tutorial. The tutorial already runs more than 30 minutes, and I think your brains might be full by now. So give yourself a pause and stay tuned while I create part 2 and finish the effect. And now it's time to really thank all our patrons, especially
Part 1, all right. Polyfolding part 2. Is polyfolding part 2. Oh, another 30 minutes. Ugh. All right, let's go.
Hi, welcome to part 2 of the polyfolding tutorial. Last time we left off with the build system node. We created a metric for these primitives to be able to find parents for each individual primitive and form parent-child relationships. And then we created a matrix, a system basically, that used the edge between a primitive and its parent as the origin, or the midpoint of the edge as the origin, and 3 rotation vectors that were created from the directions of the edges. So basically we had a system that defined each individual primitive as an object. To create this system, we needed the connectivity information, so we kept the entire object a polygonal mesh. But now we want to use the information to transform the individual primitives, so we somehow have to separate all these primitives. If we turn on point numbers, you see that at the moment all these primitives are sharing their points. So for example, this point 3719 here is shared by all of these 6 primitives. What we need is primitives with unique points. So the points should be duplicated such that each primitive has its own set of points that are not shared with any other primitives. Then we can transform each individual primitive. Fortunately, we have a SOP that does this. It's called facet. So lay down a facet SOP and append it here, make it visible and check unique points. As soon as you do this, you see that you now have a lot of overlap.
Unique points.
Points, and all the font shading is gone because we don't have any connectivity in this mesh anymore. We can check this if we quickly append a point jitter to move the point around, and if you go down with a scale quite a bit, turn off point numbers, you see now we have individual primitives. That is good.
Jeez. Point jitter. Okay.
Okay, so now, how do we transform these primitives? The idea is that we want to localize the primitives. That means we want to express some points in local space. At the moment, all the points are still defined with respect to the origin of the world, although we created a system for them. Now we have to define them with respect to this system. That means we will move all the points of each primitive such that they are defined with their particular origin in mind. And if we have that, we can then use a different set of matrices to move them wherever we want. And that is exactly how chains of objects on scene level behave. So let's do that. Let's create another wrangle and append it. This time we want to use a point wrangle. Of course we want to localize the primitives, but what we have to move is the points, as the primitives cannot be moved directly. So call this localize primitive.
Another primitive wrangle, man. All right, primitive wrangle. There you are. Connect that boy. Snap it into there. Call it localize primitives.
So this is a point wrangle. But before we attach it here, we want to promote the X foreign attribute that is currently defined on prim level to points, just to make our life a little easier. So lay down an attribute promote, append it after the facet.
Okay. We want an attribute promote.
it, call it promote xform, and let's promote the attribute xform from primitives to points, like so. And now attach the localized primitive wrangle. And let's press Alt E to open the editor, and let's implement this. So let's create a matrix.
So let's
xform, and let's just import our xform attribute for add xform. Because we promoted the attribute to point level, we now can use the add syntax here inside of the point wrangle to read it. And now we want to invert the matrix, because we want to apply the inverted transform that the matrix xform defines to all the points to move them to local space. So let's create a new matrix, matrix xform inverted, and let's use the invert function. So, and let's invert xform, like so. Now we have a matrix that does exactly the opposite of the xform matrix. And now we can multiply all the points, mt times equals xform invert. So we can multiply all the points by this inverted matrix. And as soon as we do this, we get this here. We get all the primitives moved to their particular origin and rotated accordingly. And that is why you see that these primitives are all aligned with
matrix xform for xform invert xform. Invert xform. Mine didn't do that. Xform.
one of their edges, and that is the edge that connected them to their parent primitive before. And they are all moved to the origin. With the primitives in this state, we now can build new matrices to transform these primitives back to the place where they have been, and then we can alter these matrices to make them rotate. The xform matrix is the global matrix for the so-called objects. I call the primitive objects for now. And if we would apply just the xform again, they would move to their old location, but we wouldn't gain anything from this. Instead, we want to move them to their own location by a different set of matrices. We want to express the transformation matrix with respect to the parent transformation matrix. And then we want to create a chain of matrices that are transformed one after the next, always with respect to the parent. And then we will finally reach the location where the primitives have been. But then each individual primitive is defined with respect to its parent, or the system of its parent. And that means if the parent transforms, all the children will transform with the parent. And that is exactly the behavior we need for the curving effect. So the next step is to localize the xform matrices. So create a new primitive wrangle.
Okay, but I need to first get them to move. For at xform invert equals invert xform. Let's make sure I did that one right.
To the next, always with respect to the parent. And object is y equals, and call the wrangle xform from primitives 2 points, like so.
Primitives 2 points. That's what I did. Primitive 2 point. X form. Promo X form.
And now attach the localize primitive wrangle. And let's press Alt E to open the editor. And let's implement this. So let's create a matrix. X form. And let's just import our X form attribute for add X form. Because we promoted the attribute to point level, we now can use the add syntax here inside of the point wrangle to read it. And now we want to invert the matrix, because we want to apply the inverted transform that the matrix X form defines to all the points, to move them to local space, called primitives to points, like so. And now attach the localize primitive wrangle. And let's press Alt E to open the editor. And let's do it.
For at X form.
So let's create a matrix called X form. And let's just import our X form attribute for add X form. Because we promoted the attribute to point level, we now can use the add syntax here inside of the point wrangle to read it. And now we want to invert the matrix, because we want to apply the inverted transform that the matrix X form defines to all the points, to move them to local space. So let's create a new matrix, matrix X form inverted, and let's use the invert function, like so, and let's invert X form, like so. Now we have a matrix that does exactly the opposite of the X form matrix. And now we can multiply all the points at P times equals X form invert. So we can multiply all the points by this inverted matrix. And as soon as we do this, we get this here.
That's not what I get. What did I do wrong? Oh, what did I do? Oh, what the heck? I really don't know. There's that. That doesn't look like what he got though. Does not look correct. Anyone in the chat can tell me what I've done wrong here. Maybe I have to go back up into my IDX primnum. X form. For X form equals X form. So why am I changing it back to this? And I already have this thing here. Oh, I don't know what to do. Oh. Don't let it end like this. What does this lock mean? Locked. Maybe I just download their file. All right, let's just download the file because I don't know where I messed up or like what. Or like how to do whatever, so I'm just gonna go. I'm gonna resume from here. And it's all broken. Because this needs to be just neighbors. What else does it say? Did you mean neighbors? Yes. In fact, I did mean neighbors. Undefined polyneighbors. Where is that? Call the function. What function? What? Find parent, attribute VOP, 1 snippet 1, call to undefined function, poly neighbors. This one? Bro. Bro. What? It's still looking for VOP snippet 1? Where is that? What the heck is a VOP even? This one? Yeah, the one I was doing was better than this one. promote X4 and skipping unrecognized parameter. Polyfolding sphere 1 unrecognized parameter R. What? The only thing I did was change that. That's the only thing. Bro. Bro, I'm too tired for this. These tutorials, man. Well, do I just keep going? I guess I'll just keep going, even though my... I mean, getting this effect to work is not so much my goal. It's more just to learn how Houdini works. So it's not the biggest deal that I can't follow along, but I mean, I'll change it to vertices and then, or points, and see what happens after that.
We get all the primitives moved to their particular origin and rotated accordingly. And that is why you see that these primitives are all aligned with one of their edges, and that is the edge that connected them to their parent primitive before. And they are all moved to the origin. With the primitives in this state, we now can build new matrices to transform these primitives back to the place where they have been, and then we can alter these matrices to make them rotate. The X4 matrix is the global matrix for the so-called objects. I call the primitive objects for now. And if we would apply just the X form again, they would move to their old location, but we wouldn't gain anything from this. Instead, we wanted to move them to their old location by a different set of matrices. We want to express the transformation matrix with respect to the parent transformation matrix. And then we want to create a chain of matrices that are transformed one after the next, always with respect to the parent. And then we will finally reach the location where the primitives have been. But then each individual primitive is defined with respect to its parent, or the system of its parent. And that means if the parent transforms, all the children will transform with the parent. And that is exactly the behavior we need for the curling effect. So the next step is to localize the X-form matrices. So create a new primitive wrangle and append it. And call this one localize matrices. Like so, make it visible, and let's open the editor for this one. So to express each matrix in its parent system, we have to multiply the matrix with the inverse of the parent matrix. So let's create a new matrix variable, matrix, and let's call this par for parent, xform for xform, inverted. And it will be the invert function again, because we want to invert the matrix, and then we use the print function to find the matrix. With 0, the attribute to read is xform, and then as an index we use I at parent. Like so. So this is quite a mouthful. What happens here is that the prim function will read the matrix X form from the parent primitive. That is still saved to all the primitives, although they are transformed to the origin. And then this matrix will get inverted. And now we want to localize each matrix, each X-form matrix. So we will create a new attribute called for_add for a new 4x4 matrix called local X-form, expressed in parent space. And that will be just the X-form, so the global X-form, for_add X-form that we still have. And now we multiply this by par X-form inverted, like so. Apply and accept. After this step, we have a new matrix that is called local X-form. Do we? Not on the points, but on the primitives. Actually, we don't have a matrix. We don't have a local X-form and we don't have an X-form. And that is due to a stupid mistake I made while promoting. I missed to check delete original off. This will delete the X-form attribute from the prim level. And that and of course we don't have an X-form anymore and we cannot create a local X-form from it. As soon as I uncheck this, I have X-form here and I still don't have local X-form, and that is due to a typo here. So X-form inf is how we call the matrix, and if we do that, hopefully finally we get local X-form. So we have X-form here and we have local X-form. And this local X-form is a transformation matrix expressed in the parent space. So in the space of the parent primitive. But we have to be careful again, because we have primitives without a parent, the root primitives. And we again have to correct for the root primitives, because this operation will not yield usable results if there is no parent matrix. So let's correct the border case again. Correct border case. And let's say if I parent is smaller than 0, so whenever it is -1, in this case, let's create the local X-form for add local X-form, and let's make it just the global X-form. Because in the case of the root primitive, the global X-form is what we can use. And there is no parent. Okay, now that we have that, we work in the order case. So now finally we created local matrices from the global matrices. We have a matrix that defines the object in parent space for each individual primitive. And now we want to multiply all these local matrices together to create global matrices again. But this time, these global matrices will be composed of a long chain of linear transformations. We will start with the root primitive, and then we will apply one local matrix after the next until we reach the primitive. So the primitives will move to exactly the same locations they've been before, but not by just using one matrix, but by using a set of matrices, a chain of matrices, applied one after the next. So what we actually
I'm so lost, I have no idea what's going on at this point.
Original X-form to a lot of successively applied local X-forms. So great, but to be able to move these primitives back, we need, again, one matrix that we can apply. So let's create this matrix by gathering all the parent matrices for each individual primitive and multiplying them all together. So create another primitive wrangle, and let's call it
If you say so.
To new global, like so. Type is primitive, press Alt D. Okay, to be able to find all the parent local matrices, we first need the parents. So let's create an array parents, brackets, indicate this is an array, and then let's read I brackets at parents. The attributes story of parents array. Now be careful, We reverse this array to get rid of the -1s before, so we have to reverse it back here. Reverse. And I know that there are more elegant ways of doing this than first reversing it, then removing one index and then reversing it back. Somebody pointed out in the comments to the first part of this tutorial that pop might do the trick. But I did it in my demo file like this, so I stick to it for now. It's not very elegant, I understand this. Nevertheless, after this operation, we have our original parent array back. And now we need the global matrix, so matrix, global matrix. This global matrix will be a matrix that is transforming the point back to their original location, but it will be composed of a chain of individual matrices. So let's initialize this variable with the local x-form for add local x-form. That's the very first matrix we use. And then we need the parent matrix, parent matrix, so, and just initialize it to be the identity with the ident function. It gives a matrix that has nothing. And now we do it for each loop and go over all the parent that we have. So for each integer parent inside of the array parents, so, and now let's multiply all the matrices together. The first step is to find the parent matrix. So at the moment of the identity we have to write something useful to this variable. So let's say parent matrix is print and then 0 local x1 but of index parent. This gives the local x-form of the parent. And now the global matrix is multiplied times equals parent matrix. This line says it's a global matrix, whatever it is, multiplied by the parent matrix, and then save it to the variable global matrix again. So these two lines inside of the loop will multiply each and every parent matrix on top of the other matrices until a root primitive is reached. So after this loop, we have a new global matrix. And we want to write it back as an attribute, but only if this is not a root primitive again, because a root primitive should just use the global matrix. So let's create an if statement. If I add parent, and this time we say if bigger than -1, because we want the code block only to be executed if this is not a root primitive, brackets. And here we say for add local x-form is global matrix. So, and this is again a little distracting because I am reusing the attribute local x-form. It would be a lot clearer if I would create a new attribute, but then we would save the third 16 float matrix as an attribute, and this costs a lot of memory, so that's why I'm just reusing local x-form here, although it's not storing the local x-form anymore after this step. Let's see if we have errors. Press apply and we have an error, and the error is here, parent matrix is not 0. Accept. Okay, now after this step, the attribute local x-form stores in fact global x-form again, but this global x-form is composed of all the local x-forms, and that means that later can go in here in
is
do something to the local x-form before it gets multiplied together again, and that means we can influence these local x-forms and we can rotate or scale the individual primitives before they get transformed back to their location. The next step is to actually use this newly created matrix to transform our primitives back to their original location. So another wrangle, this time the point wrangle again, as we intend to transform the points, point wrangle, like so. And let's call this wrangle x4 points.
Another
And let's abandon
primitive wrangle, attribute wrangle. Wait, is there a primitive wrangle? Is that why I messed up? Attribute wrangle. Is that the same as a primitive wrangle? I think it's the same thing, right? Looks the same.
now inside of this wrangle. Control D to open the editor. And inside of this wrangle, let's first get the primitive that holds the local x form. Because we are on point level here, it's a point wrangle. And that means to read the attribute local x form that we created on primitive level, we first have to find the primitive that the point is attached to. So let's say int my prim, and this will be an array as I intend to use the function point prims.
An array.
Which gives all the primitives attached to a point. Black brackets. And the geometry string is 0. And we want to find the primitive for the current reference point. Num. Like so. And this gives all the primitives the point is attached to. But as we unique the points, this is only one primitive. So we just can use the very first index of this array. And now let's create a matrix variable called local x form. And let's read the print function of string 0. The attribute is called local x form. Like so. And now we just use myprim and then index 0 as the index. And that's the very first primitive the point is attached to, so this will work. Now this gives the local x form of the primitive the point is attached to. And now we can just write a p, again, times equals, so we multiply the point by the matrix and then store it back to the point. And we want to multiply it by local x form, like so. And if we don't have errors, in C works, we get our object back. So
Now I have an error. Int myprim equals point prims 0 at pt num matrix local x form equals prim. Oh, here we go. Hey, it's almost back. Half of it's back. I'll take it, dude. We take those. We fucking take those. Hey! It's halfway back. We can work with this.
a lot of work for nothing. We started with that
all that work for nothing is right.
Wrangles with all of this code, we have exactly the same result, but with a very important difference. And that important difference
The
is
connection
that
between the
these
polygons.
locations are now reached by a chain of matrix multiplications. And that means we can implement something in between here to alter these transformations. Okay, now the fun starts. We finally are able to do something with our setup. And for this, we guessed it, we need another wrangle, a primitive wrangle. Primitive wrangle, and let's call this rotate. And because it's so important, maybe just color it red or something. And put it here in between localized matrices and local to new global. because we want to change the matrices
How do you make it a color?
before we rotate. And because it's so important, maybe just color it red or something.
Color, how did he do that?
Rotate. And because it's so important, maybe
C, color palette.
just color it red or something. And put it here in between localized matrices and local to new global. Because we want to change the matrices before we combine them to form new global matrices. Like so. Open the editor and let's finally implement the rotation code. So the very first thing we'll need is just an angle, and let's create a parameter for this. So float angle will be channel, let's call it angle, like so. And to make it more user friendly, include all of this in brackets. And let's use the radians function on it. That means that the input can be in degrees, easier to read. Press apply, and if you now go to this little button here in the parameters window, the angle will be created. Maybe to be able to change it in the right parameter range, go to edit parameter interface and change the range of our newly created angle parameter from the ranges in the here in the parameters window. The angle will be created. Maybe to be able to change it in the right parameter range, go to edit.
Edit parameter interface.
Parameter interface and change the range of our newly created angle parameter from minus 360 to 360. So apply and accept. Now we can input the whole angle range. And now we want to rotate the local X forms. And we can do this by using a rotation matrix. So let's create a rotation matrix. So another matrix called rotmat, and let's initialize it to the identity again, ident. So now let's use the rotate function, which rotates a matrix by an angle and axis, and let's rotate the matrix rot. It should be rotated by angle. The axis to use should be the x-axis. So just give it a vector here, and be a static vector 1, 0, 0, which is the x-axis, like so. And this will actually create or set up a rotation matrix that does a rotation around this axis by this angle. And now we can apply this rotation matrix. But again, we only want to apply it if we are not dealing with a root primitive. So, same code as before. If I add parent is bigger than -1, only then stuff. And the stuff to do is let's alter the local X form. So for add local X form, and this should be the rotation matrix times the old for add local X form. And we want to multiply this matrix from the left. That is why I'm writing like this. So let's press apply and let's see if we have errors. And if we don't have errors, now by altering the angle, you see it's working. All
Yes.
strips are curling.
It's working. No.
And they are very sensitive to the angle because the angle is applied to each individual primitive. So let's decrease
Oh.
in smaller increments, like so. And you can see what happens here is that now these strips are curling, actually.
Dang it.
So what's happened is that all transformation matrices that are all
So
defined
doing
in
something.
parent space get this rotation of, at the moment, 4.77 degrees, or minus 4.77 degrees. And all of these rotations add up to form this curve. So it starts with the primitives and then it curls up because
I got to do this.
it's rotated inside of its parent system.
Oh man.
And this gives this nice curly
Boom!
behavior.
How about that effect?
And you easily can imagine that this setup is very powerful because now we have control over the entire transform of each individual primitive, and not only that, of hierarchical strips of primitives. So we can apply transformations.
It's a good first attempt at a tutorial. I don't know where it went wrong. I was looking.
Another effect is working, but we of course don't want to apply the same angle to all of the primitives. We want to animate the effect, and that means only applying the angle to the primitives that are currently growing. So let's introduce another node to animate the effect. And for this I will use a bob. Primitive.
VOP. What does VOP stand for?
Let's call it animate. And let's color it red too.
Grizz, no, I can't explain it, Grizz.
Correlated with a rotation.
I'm just following a tutorial.
And let's dive inside.
Basically what you do is you set up all these bad boys to select, like you're defining how you're selecting the polygons and how the polygons are connecting to each other. But I messed it up somewhere, so you're pretty much building your own effect. Like in Cinema 4D, it would be like you just have all of these effects built into there, but like this one, you're building an effect from scratch, which is pretty cool. And I really have no idea how it works. Like he explained it all, but I would never be able to go back in here and recreate this effect just by memory. Mainly because I don't understand the code syntax. Like I get it generally. I understand, okay, you're defining variables, you're creating some loops. You're saying, okay, I want to select these and I want them to behave in this certain way. Like I'm creating a vector, which would be, looks like you can create vectors, integers, and matrices. The vector, well, I know the integer would be, I know the matrices have multiple values. Like a matrix can holds more than one value. The vector origin takes edge position, point. Oh, like these are functions. So there's different functions you can do within this language, which I think this is Vex. But this is my first time using it, so I can't even explain it that well. Or at all. I don't even know what I'm doing. I'm literally just following this guy's tutorial.
Okay, so the idea is that I want to use the distance attribute we created at the very, very beginning of the tutorial to drive the animation. I want to remap this distance between 0 and 1, but only use a certain range of it. If you remember here, we had this attribute that is a gradient, an attribute gradient over the entire object. And now I want to just take a certain range of it, say between 0.1 and 0.2, and remap it to 0 use it as an animation parameter. So inside of the VOP, let's first bind the dist attribute. Dist. Here we have it. And now we need a fit range. Because this distance here has a distinct range, but we only want to use a subrange. And which subrange is that? Well, let's define it by using parameters. First create a parameter node.
Oh, I'm missing it. I'm not paying attention. Alright, go back.
To indicate that this is
It's almost over.
Position parameter. Use it as appetitive. If you remember here, we had this.
Maybe I did this part last night, and that wasn't even set up right. So maybe it's like at the very beginning I messed up somewhere.
An attribute gradient of the entire object, and now I want to just take a certain range of it, say between 0.1 and 0.2, and remap it to 0 to 1 to use it as an animation parameter. So inside of the VOP, let's first animate the effect. And for this, I will.
I gotta put it up here. VOP network. A primitive VOP. Okay, let's move these boys down. You can't see that. It's underneath. Here, let's do this. So a primitive VOP. Primitive VOP. Pop that in there.
Let's call it animate. And let's color it red to indicate that this is correlated with the rotate node. And let's dive inside. Okay. So the idea is that I want to use the distance attribute we created at the very, very beginning of the tutorial to drive the animation. I want to remap this distance between 0 and 1, but only use a certain range of it. If you remember here, we had this attribute that is a gradient, an attribute gradient of the entire object. And now I want to just take a certain range of it, say between 0.1 and 0.2, and remap it to 0 to 1 to use it as an animation parameter. So inside of the VOP, let's first bind the dist attribute. Dist. Here we have it. And now we need a fit range. Because this distance here has a distinct range, but we only want to use a subrange. And which subrange is that? Well, let's define it by using parameters. First create a parameter node, and let's call it position to indicate that this is a position in the attribute gradient. And then let's create a second parameter, and let's call this one width.
Oh, in here. Alright, two parameters, position, width.
Because that is the width of the area that should be transformed to 0 to 1. So now, let's connect the position to the source minimum. So this number here will be the value
position to the source minimum.
And everything that is less than this number will be 0 too, because this fit is clamped. And for the source max, let's use an add. And let's add the width to the position, like so. And now use this as the source max. That means the position plus the width value will determine the value on the attribute gradient that will be 1 after this operation. And everything that is bigger than this value will be 1 as the fit is clamped. So now we have our animate value. Time to bind it. Bind export. And call this attribute animate. So, okay. Now let's go up one level and let's dial in the
Okay, hold on.
set value. Type the value. Find export and call this attribute animate. Like so.
Hold on. All right, animate. Then here.
Okay. Now let's go up one level and let's dial in the width of say 0.3 and let's see what this gives if we go to the geometry spreadsheet and to primitives and say view, hide all attributes and then animate. We see that we at the moment
And then go to view, hide what?
have a value. Let's dial in the width of say 0.3 and let's see what this gives if we go to the geometry spreadsheet and to primitives and say view, hide all attributes and then animate. We see that we
Okay.
at the moment have a value of 0.875 here, and if we change this, you see it is working. Maybe we can even try to visualize it. So lay down a visualizer and visualize. And of course we have to put this later in the chain, otherwise nothing will be visualized. And let's visualize animate. For now, deactivate the rotate and see what happens here. You see, this animation thing will happily move over the object. Can go bigger than one, and then it will move entirely over the object. Great. This can be used to drive the rotation effect. So let's get rid of the visualizer and reactivate the rotate. But to use this value, we have to alter the code of the rotate, because at the moment only the angle is determining how much each primitive should rotate with respect to its parent. But by adding one line of code, we can change that behavior. Here we read the angle from the parameter. And now after that, let's write angle times equals at animate, like so. And that means please take the angle that comes in from the channel, but then multiply it by the animate attribute and store it back to angle. And if we do this, apply and accept, we now
Oh
have
my god, I was paying attention. It's almost over. Keep focus, Gabe.
add primitive and reactivate the rotate. But to use this value, we have to alter the code of the rotate, because at the moment only the angle is determining how much each primitive should rotate with respect to its parent. But by adding one line of code, we can change that behavior. Here we read the angle from the parameter. And now after that, let's write angle times equals at animate, like so. And that means please take the angle that comes in from the channel, but then multiply it by the animate attribute and store it back to angle. And if we do this, apply and accept, we now have animation control. But it does strange things, and that is due to the fact that the values are inverted. At the moment, all the primitives get the rotation angle set. So let's revisit the bob and just change the destination min and the destination max. So we want a 1 here and a 0 here.
Oh, the fit range. Wait, do where now? Fit range. Fit 1. Where is this panel?
At the moment, all the primitives get the rotation angle. And now all the primitives get a value of 0, but that we just need long and complicated tutorial. Back, but that all the we want to get the rotation angle set.
Where is that? Oh, the fit. Oh, here, okay. 1, 2.
So let's revisit the bob and just change the destination min and the destination max. So we want 1 here and a 0. And now all the primitives get a value of 0, but only the ones where the animate value is 0, they get a value. And now we just animate this value back. And you see, it is now working. It goes up and then it closes the object. And I think this is pretty neat.
No, that is neat. I wish it worked for me. I wish I
this long and complicated tutorial. Of course, you can extend this effect by any means. You could go to the rotate.
I wish it worked for me. That would be cool.
And add scaling here. So create a second.
But I did learn a lot doing this for sure.
And then create a scale matrix here and multiply it with the transforms. So you pretty much can do whatever you like with the transforms of the individual primitives. So basically what we created is the same thing as in rigging, where we have chains of bones that are transformed in parent object space. We have chains of primitives that behave like bone chains. And so we can make them curl, we can make them scale. We can basically make them do whatever we want. So thank you a lot for listening. It was fun to do this. I hope you learned a lot. Thanks again and see you next time. And now it's...
Okay, that was a good tutorial for sure. I'm not going to go back and troubleshoot it because I don't think that's really worth the time. But yeah, what tutorial should I do next? So we did part 1, part 2, analytical foam. Now that looks like it could be fun. That looks like a fun one. What else we got? Analytical foam. We're gonna have to save one of these for next time. Because I think I'll end it here. But yeah, I'm gonna keep going through these tutorials. Procedural snowflake. I want to find one where I can get something to like grow through geometric deformation. If that makes sense. I want it to like multiply the geometry or do something like that. In some interesting kind of way. There was one that you could like build fractal pattern that I was watching. So reaction diffusion theory. But I think that any of these I watch, I'll be able to pick up some stuff. Just because of how new I am to Houdini. Oh, is that what Photoshop used to look like? I totally forgot. Loops and subdivisions. See, some of these are a lot shorter. The one I watched was like...
The triangle should be...
Well, this one's longer. But the one I just watched was like an hour-long tutorial. Yeah, I think something like this. So yeah, I'm gonna end it here, but there's also another program I would like to check out, and I might as well do it on stream. And it's called Notch. And this is more for, it's 3D, but more for real-time graphics and like live performance, which I'm very interested in. So I think I'll start digging into that, and I'll do the same kind of thing. Maybe I can go back and forth between like Houdini and then Notch, that kind of thing. So I go back and forth. But thank you for watching, and we'll see you on the next